Hi, welcome to video 2 for Humber UTC's revisions for R109 Engineering Materials, Processes and Production. Alright, we were looking at question 1 and we were moving on to question 2. But this video session really I want to talk about revision. I want to talk about how you can prepare yourself with knowledge for all of these questions. Not so much preparing you with knowledge, but actually revising the knowledge that you've already been given. So I was looking at question 2, and it talks about give 2 properties of copper that make it suitable for making electric cables. Previously, I mentioned something called ToedsFM. This is a mnemonic. This is a set of letters turned into a phrase that helps me access memory, draws in my knowledge and understanding. Now, ToedsFM actually expands out into sets of pairs of properties of materials, and this then allows me to access lists of information with regard to different metals, polymers and other and smart materials, and I'll show you how it works. Basically, put that to one side. I've started one here, so we've got a piece of paper, and basically all I've done is I've folded it into 4 columns. One column for the properties of materials, and you can see here I've started to work on those properties of materials, and then a column for metals, a column for polymers, and we don't use the term plastics, the official term is polymers. Plastics actually comes down here, it's a property of material rather than an actual material in its own right. And this sort of A5 sheet then is going to contain a huge amount of information about the metals, polymers and other smart materials and their properties, and it's going to help me in the exam, because when I'm sort of trying to remember something, I can remember this sheet and I can remember the layout in the columns and where the positions of information are. It's actually believed that memory can be what's called positional, so you can remember the position of something in a room or position of something on a page, and that actually helps you access that piece of information. So that's how this actually works. So if I go through and have a look, I've got one started. So here we're talking about thermal. Thermal is to do with heat, and what we're looking at is, does the material conduct or is it an insulator? Optical properties, is it clear or coloured? Translucent, opaque are other words that you can use. Transparent. Again, electrical, is it a conductor or is it an insulator? Density, is it heavy, is it light, does it float? Stiffness is one. This is probably better for year 12 and year 13, which to do with something called the Young's modulus of elasticity, which sort of relates to elastic and plastic down here. So I don't need to worry about stiffness too much. Fusibility, to do with becoming molten. Some thermoplastics have good fusibility, they become molten and then can be reheated and reshaped. Magnetism, only really ferrous metals are magnetic in the basic sense of the word, so a way of identifying ferrous metals would be through magnetism. It's a property that we have to be aware of. So these are physical properties, and then we have what's called the mechanical properties. And we pair these off, so we create them into little pairs, so hardness and toughness work together. Something can be hard and tough, or it can be hard but not tough. For example, glass. Now glass would go in this column here under ceramics, and you'll see that a little bit later. Glass is very hard, it's scratch resistant, it resists indentation, but it isn't very tough. Glass can't absorb an impact, it would shatter. So hard and tough sit together as a pair there. Then we have malleability and ductility, elastic, plastic, creep, fatigue, environment and sustainability. So in total there we have 17 properties. I'm going to have a quick look at these lists and then we'll start looking at our materials. So, malleable. Malleable. Now, malleable and ductile are similar but different. Malleable is compression. Can it be changed in its shape through compression? E.g., if you hammer it, it can be changed. Whereas ductile is tension. It's stretching it out into a wire. So I'll put wire there. So malleability is when you hammer it and it's got good malleability, and ductile is when you can stretch it and tension. Now it seems odd, and you would think, well, for example, copper has very good malleability and very good ductility, and this is why we can create copper wires. Whereas aluminium is quite malleable, but actually it's not as ductile as copper, so it has one property but not the other. Elastic is exactly that. It's something that springs back. Things can have elasticity. It springs back into its shape. Quick example, you've all heard this sound before. A plastic ruler is back into shape. It has good elastic properties. Plastic is the extreme of that. It's where when you've changed its shape, it maintains that new shape. It's plastic. So that for example, if you bent a wire, that wire would be plastic, which is odd because it's made of metal. Which is why I say polymers is the proper word for plastics. Plastic is a property of being bent and maintaining a new shape. So I'll put a new shape there. Now, these two are very unlikely to come up in the exam, but they are properties more again for year 12 and year 13. Creep and fatigue. Creep is when it's a plastic in that it changes shape over time. These are both time constant ones. Shape over time. And fatigue is when the material becomes tired. If you're constantly flexing something, flexing, it will become fatigued. The material will be worked. You've done this with a paperclip. You keep bending the paperclip, and then eventually it just sort of snaps very easily. It's because the work becomes work hardened and it becomes tired or fatigued. Then we have to think about the material's environment. Is it environmental? Does it have an impact on the environment? For example, polymers are made from oils, and therefore they'll have an impact on the environment because you've got to dig that oil up out of the ground, or you've got to sort of go out to sea and get oil. And the other thing is the material sustainable? Can you keep going? E.g., renewable. Okay, so ToedsFM, 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 and then you remember these in pairs. So hardness, toughness, HT, MD, EP, CFES. And you will have to sort of just learn this, commit it to memory with a little bit of practice, and you'll see how you can do practice a little bit at the end of the session. This will start to become much, much easier. You'll start to be able to remember these. So hard is scratch resistant, tough is impact, malleability is compression, ductile is tension, e.g. making a wire, elastic is that it's springy, plastic is that it's not springy, it bends and it has a new shape and it can't get back. Creep is that it changes its shape over a long period of time. Fatigue is if you keep flexing it, eventually it snaps because it becomes tired or fatigued. The environment is to do with the material's impact and whether it has a negative impact on the environment. And sustainability is whether you can sort of keep using it, you know, is it renewable or recyclable. And that is our properties. And the next part of the system then is to start structuring your knowledge of the different materials. And we like to work on a rule of 3. So we go 3 by 3 if we can. Okay, so what I'm going to do now is I'm going to work on this 3 by 3. So we've got 3 columns for 3 types or 3 categories of materials, and then we divide each of these into 3 sections and then start filling in. So I'm going to pause it for a second and just lay out this structure so you don't have to watch me do that, and then we'll start filling in boxes. So here's the structure I was talking about, and here's how it works. We're basically going to just list 3 ferrous metals, then 3 non-ferrous, and 3 alloys. And there's a line underneath each one where you're going to put an application, a use for that particular material. So then you've got your properties, the material and the application, the use. I've also introduced a bit of colour. So in addition to memorising where on the page your piece of knowledge sits for a particular material, I'm also starting to introduce a bit of colour, so to help you differentiate. So when I think about ferrous metals, I'll be thinking about blue. Non-ferrous, well, stop, non, so I've used red. And alloys, I've used the mixture to create the idea of sort of green. And I'll sort of repeat this in the other columns. So let's look at metals. Ferrous metals. Ferrous is to do with iron. The symbol is Fe. So we don't just say iron though, because there are different sorts of iron. The key one that we need to remember is cast iron. Now cast irons for use for things like, it can be saucepans, it could be manhole covers. So I'm going to put it down here, saucepan, and also manhole. I know it's a manhole cover, just manhole would be good, because that fits on my page. Now, another ferrous metal are the steels. There's mild steel, tool steel, high speed steel. So I'm going to put steel here. Okay, and then in brackets I'm going to put, there's mild, tool, and high speed steel. And then I'm going to choose an application, a use for steel there. Then I'll put a common use for steel here. Finding other ferrous metals is a little bit difficult, so I'm going to use an alloy. So a little star there, and put stainless steel. So I've got a pattern of 3. 1, 2, 3. Now what would you use stainless steel for? Well, I'm going to leave these blank. And the idea is that we're going to fill this sheet out, but I'm going to leave the application of the jobs blank for this video, and you're going to take that away and you're going to fill yours in, and then the next video we'll do a comparison and see what applications you came up with and what applications I've got on my list. Now there isn't a right or wrong answer, it's just that will give us more information about the different materials. Okay. So non-ferrous metals then. The go-to one, aluminium. Copper is always a good one. And then there are lots. You know, you've got the precious metals like gold and silver, which, you know, gold's very good, it's very conductive. It has good electrical conductivity. You could look at the sort of the high grade materials. Titanium is one that comes up occasionally. Yeah, that's really, so it'd be interesting if you can find an application. That's very strong, very stiff, very lightweight, hard and tough material. Looking from a green pen. What alloys could we look at? We've got stainless steel already, so we've got a bonus alloy, if you will. We have to think about sort of some of the other alloys, and I find an alloy for aluminium, an alloy for copper, possibly an alloy for titanium. I'll come back to that in a minute. We'll just have a think. So, an aluminium alloy, I hope you can read this, is dural This is one of the earliest aluminium alloys, duralium. An early alloy, it's a trade name, and it's for age-hardened aluminium alloy, and it's 90% aluminium, and interestingly, it's basically aluminium and copper, so it's these two. So we've got a alloy for both of our first two non-ferrous pure metals. It's also got a little bit of magnesium in it, and manganese, and it's a really hard alloy, so it's a good one to choose for aluminium. And now one for copper. one of my favourites is brass. Brass is copper and zinc. It's got very good electrical conductivity. You find it in plugs and things like that. I just like it. It's a very nice. It's very workable. It's easy to work with, and it's a good conductor, and it's very hard. It's got a good resistance to scratches and indentations. And I'm going to put bronze. Bronze is one of the oldest alloys known to man. It's one of the earliest, hence the Bronze Age, if you're studying history. Bronze being a mixture of copper and sometimes these days not so much, but it used to mostly contain tin. But bronze contains lots of other, and this is the thing with alloys, they tend not to contain just one or two materials, just the two materials mixed. They tend to be sort of complex metallurgical combinations. But for simplicity's sake for the exam, if you learn duallium, brass and bronze, and remember you've also got stainless steel, and later on we're going to have a shape memory alloy, which is a nickel and titanium. You're going to have a multiple possibilities coming off the one sheet for different materials. So, and what you need to do is you need to go away and you need to find, for cast iron I've got saucepans and manhole covers, so you need to find an example for say mild steel or tool steel or high speed steel, an example for stainless steel, an example for aluminium. Remember this is pure aluminium, not the alloys. An example for copper, an example for say titanium or whichever metal you want to put in that slot, and then for your alloys, what's an example for duallium, an example used for brass, and an example used for bronze. And if obviously you want to change any of these, feel free to do so. While you're doing that, I'm going to fill in these other two structures. So, hopefully you found some examples to fit onto your sheet. We'll look at thermoplastics now. So I've done this in red, and the idea being is that these respond to heat, and red makes me think of heat. So I'm looking for ways of sort of accessing my memory by creating memorable colour association. These reheat, reshape and recycle. So I want one there, one there, one there, with an example for each. So if you think back to the exam paper that we looked at, and we were asked for name 3 thermoplastic materials. So my first one, my go-to material is polythene. So I'm going to put that in there. Polythene. And you get LDP, low density polythene, for bags. And you can get HDP, high density polythene, for bowls, like washing up bowls and things like that. ABS is quite a popular one there. ABS is there in that question, and it's acrylonitrile, butadiene, styrene. So it's a one that's common to the examiners. So we'll put ABS in there. And again, I'm going to leave that blank and let you go away and come up with some answers to what you think ABS should be used for. I like polypropylene, but I'm going to go for a different thermoplastic, one of my other favourites, polycarbonate. And I like polycarbonate because it has excellent transparency, it's got really good optical properties for clarity, and it's also, polycarbonate has good hardness and toughness, so it makes it very suitable for a specific application, which is good for engineering. But again, I'm going to leave you to figure that one out. Now for my thermosets, I've switched to blue because these are good to resist heat, they're good insulators, so blue being cold, and thermoplastics red hot, thermosets blue for cold. So I'm going to have one there, one there and one there. and I'm going to go for urea, formaldehyde. There. I'm going to go for melamine. Again, that's a formaldehyde. Trying to save some space there. And I'm going to go for polyurethane. I like polyurethane, it's one of my favourites. Again, polyurethane's skateboarding wheels. If you've done a bit of roller skating or a bit of skateboarding, you might be familiar with urethane for your wheels. So you could put in there skateboard wheels, or you could find a different example. So I'm going to just draw a little skateboard there. That's my example. And again, this is your revision sheet, so you can do it any way you want. You know, the colours, you can use little cartoons or anything that helps you remember the information. And we'll finish with the elastomers. These are basically elastic polymers. So they're stretchy, they're the rubbers, and you get natural rubber. They're usually not pure rubber, they're a bit like alloys, they're often mixed with things. So you find a use for natural rubbers. Silicons, like silicon seal for your bath, etc. So silicon's there. So I'll put a mark there for you to find a use for it. And TPEs. These are quite new. They are, unlike these two, these natural rubbers and silicons are both thermosets, if you will. So maybe we're going to put a blue circle around those. So they're thermosets. So once you've got them, you can't. So things made out of natural rubber or silicon, you can't recycle them. Whereas TPEs, these are actually thermoplastic elastomers. So they are rubbery material, but they're recyclable. They can be reheated and reshaped. So thermoplastic elastomer. Okay. You need to find an example of how that might be used. You have to do a little bit of research to fill that in. And then we'll start on the next structure. Okay, hopefully you've identified some plastics. So I'm switching over now to the final column of materials, which is ceramics, smart materials, and composites. Okay, and you'll notice I've again switched colours. Didn't really think the ceramics needed a different colour, so I've gone for purple for ceramics. Smart materials, I've managed to find a Bic pen that's sort of a different colour. The colours aren't important, it's up to you. It just helps, it's just another thing in the memory. You remember the position on the page, and then you start to, if you practice a little bit and you keep to the same pattern, you start to create a sort of a strong memory of where things are on the page. Okay, so we're going to look at ceramics, smart materials, and composites. So, ceramics are basically they're inorganic, non-metallic, crystalline type structures. Sand and silicon can be used. They're clays, they're pots, so you've heard of ceramic pots, etc. One of the most obvious ones is glass. Glass is basically silica, sand, soda lime, some chemicals that's been melted, so it's got applying fusibility. I'm just pointing over here off the page. It's applying fusibility to create material. So glass, toughened safety glass, etc. Lots of different examples of how we use glass, car windscreens, etc., etc. So as a ceramic, glass is one of our main ones. You need to find an application for glass. Ceramics are very interesting materials in that they are extremely resistant to heat. So although you can create them using fusibility, clay tiles and that sort of join together through a process of what's called sintering, and they produce materials that are really, they have excellent what we call heat shock resistance, so they can resist a rapid change in temperature. One of the classic examples of a ceramic tile was used in the tiles underneath the shuttle, the space shuttle coming through the atmosphere. High amounts of friction on the surface really heat up, but it can resist the sudden drops in temperatures as it comes through the atmosphere. So they're very shock resistant with regards to heat. And there are actually engine blocks now, parts of engines that are being manufactured out of ceramic materials, because they have this very good thermal properties. So again, a little bit of research there would give you an example of what you might use for ceramic tiles or ceramics as a material. And the final one is, there may be a little bit of debate about this, which is a metal. Carbide, basically carbon. Now it's referred to, tungsten carbide is referred to as a ceramic, but the key thing is not to worry about that. Tungsten carbide fits on our ceramics list, and tungsten carbide has some excellent properties with regards to its hardness. We often get tungsten carbide used to manufacture bits for tools such as the milling machine, in replacement of high-speed steel. Tungsten carbide is an extremely hard material used for making cutting tools, etc. So, and it fits within our ceramics. But there is that question, is it, because it is basically in the majority a metal in a particular format, but it's in our ceramics list, and you can memorise that one and find an application for that, such as milling machine bits, etc., to be part of your memory. Right, so we move on to smart materials, and the first one that we're going to look at there is SMA, shape, memory, a bit cramped here, alloy. So shape, memory, alloy. And the one that I mentioned earlier is nickel, titanium, alloy, nitinol. Shape memory alloy is the most common format is a wire, and the wire is has very good stiffness properties, but it's also got an interesting property in that if you bend it and misshape it or twist it in any way, if you then heat it, it will remember, it has memory of its original shape, and it will spring back into that shape. It's worth doing some research and watching some videos on a shape memory alloy before you decide what example that you're going to research. So as a smart material, as a metal, as one of the alloys of nickel and titanium, then you've got shape memory alloy as one of your smart materials. Okay. So our next example is thermochromatic. I'm just going to put pig here, I can't fit it in. It's basically thermochromatic pigment. Yeah, it's colour that changes, so it's thermo for heat, chromo for colour, pigment. So it's the heat changing colour. So what could you use that for? What example could you find for thermochromatic pigment? Okay, so shape memory alloy there, an example, thermochromatic pigment, do some research, heat changing colour. I've seen some toy cars and some toy animals that have this thermochromatic pigment, and when you put cold water on them, they change colour, and when they heat up, they change back to their original colour again. Okay, so our final smart material that we like is QTC, quantum tunneling composite. So I'm just trying to fit quantum on there. And this is to do with electrical conductivity. It's basically a composite material of metals and a polymer where when you apply pressure, metal particles being closer together sort of allow an electrical current, so it becomes less resistant as you apply pressure. but again, do a little bit of research on quantum tunneling composite so you can put an application, you can fill in the application there. So that brings us on naturally to composites in themselves. So the composite materials, and sometimes students get alloys and composites mixed up. Alloys are a mixture at a sort of an atomic level. You can't see the difference. It becomes a new material, if you will. Whereas composites, you can still see the separate, the materials that are combined to make it up. So when we talk about glass fibre, I'm just going to put RP, reinforced plastic. Basically this is an epoxy resin. Now an epoxy resin is a thermoset, hence the use of the blue. So we have glass fibres, strands of fibre made out of glass. Glass is, yes, hard, scratch resistant, and we think of glass as not being very tough. So we have this material here, glass, which is not very tough because it would shatter. But actually, as a thin fibre, glass is very, very flexible and very, very tough. So it can absorb impact. Whereas thin epoxy resin, as a hard, thin plastic, it isn't. It actually is hard, but it's not tough. So the glass fibres bring toughness, and the epoxy resin brings hardness. So we've got tough, hard, combined materials to give us a very lightweight, tough, hard material. Interesting applications, have a search around for those. And very similarly, we have, it's more well known these days, we have carbon fibre, which is very popular. A little bit more expensive than glass fibre, so we have carbon fibre reinforced plastics. Now again, we've already got quantum tunnelling composite, but think of that as a smart material. So for our composites we have glass fibre, carbon fibre. Okay, and we now need to think about a final composite material. From an engineering point of view, reinforced concrete sometimes is discussed because it is definitely an engineering material, so reinforced concrete. And this is basically concrete as a matrix, like the epoxy resin is the matrix and the glass fibre are the fibres. In reinforced concrete, the matrix is the concrete and the reinforcement is usually steel bars, what we call rebar, reinforcing bar, steel bars in reinforced concrete. Again, do some research and find an application for that. So I'm going to stop that video there. There's your sheet with all your information on it. Writing it out like that gives it structure. You memorise the position also on the page, you start to respond to colour, and it's a case of practising this. So once you've filled in all the applications, I'll start to show you how you can use this in answering your exam questions.